Okay, so good afternoon to everybody. I am Piermarco Cannarsa, and I am happy to chair this colloquium at the University of Roma Tor Vergata by Michael GHIL. First of all, let me remind you to mute your microphones. And if you have to ask questions, you can always send a note, and there will be room for questions at the end of the talk. Let me just introduce our speaker, who was supposed, in fact, to give this talk in April and in Rome. and then things, unfortunately, went wrong very rapidly. But I'm glad we managed to make up this way, and of course we will be happy to restore the traditional invitation as soon as possible. So Michael GHIL, if you look into Wikipedia, you will find of Michael a definition like an American physicist focusing in atmospheric and oceanic sciences and climate dynamics. Well, that may be correct, but maybe needs some elaboration, deserves some more elaboration. So Michael graduated, he's American, graduated from NYU, Turan Institute. He was a Peter Lack student, and he developed quickly deep interest for models, well, in climate and geosciences, and in fact, all his career was well, a progress into this kind of disciplines. He is currently distinguished professor at UCLA and at École Normale Supérieure in Paris, and until now, I mean, during his career, he covered an enormous number of important responsibilities in directing geosciences departments, environmental research institutes, all sorts of teams and committees on climate. Also, he received many awards in his career. Too many to list. He is members of he's a member of a number of prestigious scientific academies, and he has an overwhelming publication record, both for quantity and quality. But I like to think of Michael, introduce him as the father of modern mathematical modeling and analysis in climate sciences. So today we'll be happy to host his talk, which will be on non-autonomous and random dynamical systems in the climate sciences. Please.
Thank you very much, Piermarco, for leaving me a little bit of time to give my talk. I apologize for all my friends and former students who haven't gotten around to expand that Wikipedia article, you know, that was written by somebody at UCLA that I don't know. Anyhow, so I just wanted to emphasize that while normally in this Microsoft Teams setting, questions have to be at the end because it's difficult for me to interact with the audience. I would like to ask Fabio to allow questions because in the United States we are used to being interrupted. It gives me a feeling that not everybody is sleeping, and I always tell my students that there are no stupid questions, only stupid answers. So if you feel like interrupting, please interrupt. But now I will start sharing my screen. Remember that I cannot see you. So the only thing that I see is my own screen from this time on. Okay, so As Piermarco kindly remarked, I would much rather be with you in Rome. You know, both my wife and I love Italy in general and Rome in particular dearly. But I hope that things will get straightened out and that we'll be able to catch up, and I can maybe give you another talk on one of the other topics that I've been working on. Anyhow, this is one of my main preoccupations these days. So the talk is based on joint work with many students and colleagues, and it includes at least one person in the audience, Stefano Galatolo, and his colleagues at Pisa, Angelo Di Garbo, and Mahangio, and Cedro, but also people in Buenos Aires, in Nice, in Reading, in Hokkaido, and in Israel. And I must have, oh yeah, there's one from University of Nevada in Reno, and somebody who's a professor at McGill. So I've been having a lot of fun with this, and I hope that you will too. So if you are interested in any of the stuff aside from the recording, there are papers. Really the best place to give you a perspective is a website at UCLA. And then, of course, there's the ResearchGate where there's much more. Okay, so the outline is, first I will tell you about intrinsic versus forced variability, and this will be essentially the motivation for dropping into this deep hole of non-autonomous and random dynamical systems. So I'll talk about multiple scales of climate dynamics and climate sensitivity, both the classical equilibrium climate sensitivity, or ECS, and the non-equilibrium one that will be interested here. So when we talk about non-autonomous and random dynamical systems, I'll introduce you to Pullback, Snapshot, and random attractors, and to tipping points. And then the climate applications will include definitely the Lorenz, the famous Lorenz 1963 convection model, but with random forcing. So, you know, the Lorenz random attractor, some of the people that I listed on the cover page call it lovingly LoRa. And then as time permits, I'll talk about applications to the El Niño Southern Oscillation, Arnold Tonks, and other things about pullback attractors. And work in progress will include non-equilibrium climate sensitivity and the algebraic topology or homology groups of LoRa, and conclude with some remarks on bibliography. So to proceed, the motivation is that the climate system is highly nonlinear and quite complex, which is sort of obvious, but with what we call in the United States motherhood of apple pie. You know, you find words like this in the introduction to the various IPCC reports, but then they're quickly forgotten as you get into the chapters. So there's much more attention given to the system's major components, the atmosphere, oceans, ice sheets, which evolve on many time and space scales, and which are modeled in great detail. But still, the predictive understanding of all of this has to rely, of course, on the physical, chemical, and biological modeling, but also on the thorough mathematical analysis of the models thus obtained. So it's what's sometimes called the forest versus the trees. So we're going to be interested here in the forest, while the great majority of people who work in the field are interested in particular trees, branches, leaves, or needles, sometimes flowers. So because of the difficulty of covering all the details on all these scales in space and time, the approach which has been pursued in the climate sciences is one of hierarchical modeling, which allows one to give proper weight to the understanding provided by the models versus their realism. So there has to be a back and forth between what's sometimes called toy models, more nicely put conceptual models, and models that those who work on the details like to call realistic, but I put that into quotation marks because, like I put the toy models, because the illusion given by the details of being realistic is somewhat of an illusion, because the details are not necessarily based on fundamental principles of physics, chemistry, etc. There are a lot of so-called semi-empirical parametrizations, where parametrization is climate modeling jargon. In other words, this is not like parametrizing a curve by arc length. It is representing in an integrated way so-called subgrid scale effects by some form of averaging at the scale of the models. So there has to be a back and forth between the story and detailed models, and of course between the models and data. So after saying all of this, the question is, can we disentangle natural variability from the anthropogenic forcing, which of course we've been hearing more and more, because it has more and more of an effect on the natural variability. So the rhetorical questions are, should we, can we? The obvious answer to should we is yes. Can we? I hope I will convince you that indeed we can. Okay, so intrinsic versus forced variability, multiple scales of dynamics and climate sensitivity. I will start here by paraphrasing John von Neumann, who probably many of you know was co-author of the first paper that demonstrated the possibility of numerical weather prediction, aside from enormously much mathematics and physics. Yes? Sorry?
No, it's a personal problem. Don't worry. Go ahead.
Okay, right. Okay, so as you know, John von Neumann was actually, it is said that Henri Poincaré was the last person who knew all of mathematics, but it is also said that when John von Neumann was asked how much of mathematics one person could know, he stopped for a second and he said, oh, about 2/3. Well, good luck these days with being John von Neumann and knowing 2/3 of mathematics. So another reason for asking questions. I'm interrupting. So aside from convening a whole group of people in the 40s to the Institute for Advanced Studies to carry out this experimental or proof of concept numerical weather prediction, he also was the motivator of a meeting that took place very shortly before his untimely death in the 50s. And the proceedings of that meeting were published as a book by Pergamon in 1960 after von Neumann's death, edited by Richard Pfeffer, but von Neumann gave an introduction to these proceedings. And this is where he said these things. So he said, the initial value problem, in other words, numerical weather prediction, that's the easiest. And that's what most people who apply mathematics to the climate sciences know about. The asymptotic problem, in other words, long-term climate, is a little harder, but it is really the intermediate problem, which is broadly known as low-frequency variability, which includes things like multiple equilibria, or if you wish, multiple fixed points, long periodic oscillations, limit cycles, intermittency, slow transients, and what's called these days tipping points, is the hardest. So this is the hardest problem which we're trying to come to grips these days. Okay, so to give you an idea again of the range of time scales, there is this synthetic power spectrum or spectral density, which is really sort of an artist's impression of the spectrum, because we do not have any time series that extend over the age of the Earth and have a resolution of days or hours. So each one of the bands in this spectrum correspond to a certain way of looking at phenomena and a certain kind of measurements. Over to the right of the spectrum, we have actually instrumental observations, but already in the middle of the spectrum, we have what's called proxy records. There are various oxygen and hydrogen isotopes in marine sediments and in ice cores. And then as you move further towards the left, it becomes sort of harder and harder. But what I would like you to notice in this spectrum is that, of course, most of the variance is in the continuous spectrum, what we call in mathematics the absolutely continuous spectrum. And then there are lines which correspond to the rotation of the Earth around its axis one day and the revolution of the Earth around the Sun, or more precisely around the mass center of the solar system, which is not very far from the center of the Sun. And then there are bumps. So the usual idea that we get in mathematics, that it's either absolutely continuous or a line spectrum, and so both of them, for instance, can be encompassed by a Stieltjes integral. Here, what's really characteristic to the climate is that these two features of spectra that we're familiar with are also supplemented by these bumps, which are, in my view, and by now that of many of my former students, postdocs, and other friends, the signs essentially of Hopf bifurcations, which result in limit cycles which become destabilized, and the lines associated with them become broadened, and so that's where the low frequency variability comes from. Note that at the bottom of the slide, it says that it is the original version of this spectrum goes back to Mary Mitchell, who published it in Quaternary Science Reviews in 1976, and it contained, this version comes from an article in the Encyclopedia of Global Environmental Change, but in the original article there was a sentence, no known source of deterministic internal variability. So this was the prevailing opinion 1 year after I got my PhD at Crown. Okay? The idea was that everything is either forcing, which gives you lines, or noise, which gives you the continuous spectrum. Okay, so we've gone a little bit beyond that. Since I took a little bit longer than I wanted with this introductory part, so you see here the reference at the, on this slide. But basically, really the concept, at least in the first few assessment reports of the Intergovernmental Panel on Climate Change, was that of equilibrium climate sensitivity, and all those complicated computer runs were analyzed in terms of such simple scalar linear ordinary differential equations. And the chapters had to do a lot with the presence of several feedbacks, positive and negative. So there were experts on each one of these feedbacks, and the sources and sinks of greenhouse gases and of aerosols. So if this view had been correct, an exponential increase in greenhouse gases should have corresponded to a linear increase of temperatures, all other things being equal, which they never are. So what we see is not this red line, but this black line, which says that we need to consider instead a system of nonlinear partial differential equations that have various, as I told you, semi-empirical parameters, which are only known within a factor of 2 or even of 10, and can be either additive or either additive or multiplicative forcing. In other words, both deterministic and stochastic effects. So this leads to an uncertainty. So this graph here is taken out of an assessment report. So again, since these Intergovernmental Panel on Climate Change, or IPCC, reports involved by now hundreds of people, they are second order acronyms. So this says assessment report number 4, and this comes out of the summary for policymakers of working group 1, the one that deals with physical effects. If you are confused, you are not the only one, because actually somebody that I'm sure many of you know, Uriel Frisch, when he read this particular summary for policymakers, said to me, well, I can't understand this. I don't think that any policymaker can. Okay. Oops. Sorry. Okay. Okay. So pretty soon we are going to be ready to do some business, but this is really pretty important. So I mentioned to you the so-called equilibrium climate sensitivity, which has its own acronym, ECS. And so the picture that I was showing you here, okay, gives you something like this plot at the top. In other words, this being time and this being either global temperature averaged over a year or CO2. So the temperature is a dash dotted, the temperature is a red solid line, and the CO2 concentration is this dash dotted blue line. So the way that this was defined in 1979 by a report to the National Academy of Sciences of the United States, it says you double CO2, what happens to temperature? Well, what happens to temperature is, of course, this. We know how to integrate scale ODs that are linear. But, so, you know, climate is a stable equilibrium fixed point. If so, mean temperature will just shift gradually to its new equilibrium value. And the delta T over delta CO2 is this equilibrium climate sensitivity. Now, on the other hand, let's say the climate were purely periodic, which would be the case if the El Niño Southern Oscillation, for instance, were purely periodic as opposed to just quasi-periodic. So that then the mean temperature will still go up, but at the same time also the limit cycle associated with this stable purely periodic oscillation could change in period, amplitude, and phase. Okay? And finally, what I call this, what about some real stuff, both chaotic and random? Well, the mean will still go up. Nobody has really come up with any good way for it to do anything else. But a lot of other things will be changing, for instance, the distribution of extremes, etc. So we want to proceed from this picture, which dominated the thinking for the first couple of decades of these IPCC exercises from 1990 to about 2010, to the more modern view of this. So this is what...
Excuse me,
Yes?
Michael. When you say real stuff, you mean coming from observation and collected data, as you explained at the beginning, or what else?
No,
real stuff.
It is exactly what you said. If you look at observations, and well, you know, there are no pure observations. Any observations get massaged one way or the other. But something that is as close as possible to the observations and contains as little prejudice of the observer, in other words, of models that are not oversimplified, will give you things that will have essentially this mix of spectral features that I was indicating here, okay? So you clearly see the seasonal cycle, okay? You clearly see the diurnal cycle, you know, it's colder at night than during the day, and it's colder in winter than in summer. That's sort of obvious, but you also see a lot of stuff that's irregular, and there are some disagreements about whether the irregular stuff comes from deterministic chaos, random processes, or both. Well, I have maybe a reserve slide at the end which says nature is not deterministic or random. You know, it depends how much you want to know about the phenomena, whether you approximate them by a deterministic model or by one that contains stochastic processes. Okay? If you take a stochastic point of view, you renounce some details, okay? You concentrate on mean, variance, maybe a few other moments, etc. So chaotic versus random is to some extent in the eye of the beholder, but I hope I'll convince you at the end that taking into account both of them is really useful. Did I answer your question?
Yeah.
Thank you. Okay, so we move now to, I actually realized that I forgot the word dynamical here, but it's non-autonomous and random dynamical systems. So again, acronyms NDS and RDS, and we're going to talk about the particular attractors that need to, how you need to generalize attractors to this situation, and about how you need to generalize bifurcation points of autonomous systems to something that's called today tipping points. Okay, so here I have a slide because there's a little bit of an argument. I'll tell you about essentially the two groups which introduced these concepts into the climate sciences, but since there's a little bit of argument between physicists and mathematicians, what is what and who did what, I have this little slide to try to clarify this. The sources of, not of non-autonomous dynamics, but of the theory of non-autonomous dynamics. So basically, you are dealing with physically open versus closed systems. Autonomous dynamics is particularly good at closed systems, okay? There is also an issue about whether coefficients depend on time or not, but let's say that they do not depend on time and that things depend largely on whether the forcing depends on time or not. So in a closed system, it's closed, it doesn't. But of course, the climate system, or more generally the Earth system, which also includes the biota, etc., is an open system. There are fluxes of mass, momentum, and energy between the system and its surroundings. We get energy from the sun, and we send it back to space, and we exchange momentum with the moon, etc. So the mathematical framework of non-autonomous dynamical system is appropriate for physically open ones. So basically, it goes back to skew product flows of George Sell, who passed away a few years ago, but whom I had the privilege to meet. And in this case, it looks like this. You have something that you call X, and something that you call Q, and the X dot depends on both X and Q does not depend on X. That's the skewness in the skew product. So X is in RD and Q is in some other space, and so Q is called the driving force for X. And then after this, so I will give the references, this goes back to the 60s and 70s, and sometime after that, we had these two concepts of pullback attractors due to, well, Franco Flandoli and Crowell and Ludwig Arnold, and on the other hand, to Chelsea-Grebogid and Ed Ott. So here you have a stochastic differential equation. I'm using on purpose another letter than here. And of course, you have, in the most general case, a variance that depends also on the state. So WT is a Brownian motion, and I don't need to tell it to this audience, but I have this for people who haven't seen a stochastic differential equation in their lives. So basically, the difficulty is that DET is proportional to dW squared, and this goes back to Einstein, 1905. Okay? So that's not new. So more generally, studying explicit time depends on enforcing our coefficients requires NDSs. The term non-autonomous is used both for the deterministic case and, you know, there's a lot of terminology here which is a little bit confusing. It is used both for the deterministic case and for a unified perspective on the deterministic and the random case. And I maybe come back to that later. The commonality between the two cases is the independence of the driving force and the semi-group property of the driving force, whether it's Q of t or W of t. Okay? This is what I didn't mention here, but I'm going to show it on the following transparency. Likewise, pullback attractor is used both for the deterministic and the random case, while in the latter case, one uses more specifically the phrase random attractor. Okay, so sorry, this slide, I forgot to change it, but it comes from a talk where I specifically applied this to the wind-driven ocean circulation as an example of a climate system. So in general, the work with theoretical mathematical work up to about a dozen years ago was done at least conceptually. It's not that people didn't use a seasonal cycle or anthropogenic forcing, but they did it like Monsieur Jourdan, you know, in Molière, who the bourgeois gentilhomme, who takes all these lessons in dancing and so on, and also in literature. And so his professor tries to teach him the difference between prose and poetry. And the reaction of Monsieur Jourdan is, oh, so you mean I've been speaking prose all my life? Okay, so likewise, when people use seasonal forcing or something else, anthropogenic effects, they did it without realizing what they were doing. Okay, so to address truly coupled ocean atmosphere behavior and climate change, an important step is to examine time-dependent wind stress or time-dependent forcing in general. Proper framework for doing so, the theory of non-autonomous and random dynamical systems. We do here with a toy model. If I have the time, I'll actually show you the toy model from that is referred to in this slide. And the forcing is deterministic, aperiodic, and dominated by multi-decadal variability in that case. But here, I'm just giving the example of the pullback attractor of a linear scalar, ODE. Okay, so we all know how to solve this. If sigma is equal to 0, it's just exponentially tending to 0. But if sigma is not equal to 0, and in particular it's positive, actually in this simple case you can compute the so-called pullback attractor. But I would like to show you, if you haven't seen this before, a little video which tells you where the word pullback comes from. So the idea is that you would like, you see, this is the sort of stuff that Carroll and Flandoli had to overcome when they started thinking about non-autonomous dynamical systems as postdocs of Ludwig Arnold in Bremen. And I've just heard this from Franco, the story during this trimester at the Institut Henri Poincaré in Paris. Pierre Marco also attended, and Stefano Galatolo. So, you know, it's not obvious what a proper generalization of a fixed point should be in this time-dependent context. So let's say that you're at time 0, and you want to know what's attracted. What is oh, so I forgot, of course, to tell you that it's very important that alpha be positive so that you have dissipation. You cannot define these things in Hamiltonian systems. So we're in dissipative system, but that's not a big bother in climate because there's enough dissipation in it to take care of a lot of stuff. So what will you observe? Well, if you do pull back to, in principle, to minus infinity, but fortunately that's not really necessary, okay? Here you pull back and you observe that this stuff, as you pull back further and further, converges to a point here, okay? You want to do the same thing over here. Again, you start, you start pulling back, and you notice that you converge to this point here. So in general, you cannot get this equation explicitly, but you can observe this behavior, okay? So we'll go back to the slides. Okay, pullback snapshot and random attractor. So again, I'm repeating here the framework of physical open mathematical non-autonomous is given by skew products and deterministic systems. And in the math literature, okay, so I should mention here also Carroll, but anyhow, the the proper definition of the sort of stuff I showed you in the little movie was pullback attractors, because of the fact that instead of dealing with a single parameter semigroup as you do in deterministic systems where you just go to plus infinity, here you have a two parameter semigroup where you have also a parameter that goes back to minus infinity. In the physical literature, they have been called snapshot attractors. So here are the references. Okay, Cowell and Flandoli, Tech Reports Scuola Normale Superiore, and then a publication in Refereed journal in 1994. Snapshot attractors, this paper by Romeras was a postdoc of Grebogi and Ott. And they coined this word snapshot attractors. And when my students and I started working on this, in other words, MICHEAL Chekroun, who was doing his PhD with me at the École Normale, and Eric Simonet, whom I had co-advised first with Roger Temam for his PhD, and then was also a postdoc with me at UCLA. We started looking at this. We were not aware of this work of, although I knew both Chelsea and Ed, and so we were aware of the mathematical literature. Okay, so one of the references to George Sell is 1967, and another one which I like very much on pullback attractors is Lai-Sun Young, what are SRB measures, and that's 2002, so about 20 years ago. Okay, so a little bit more on the theory. So basically, the theory now of random dynamical systems is a counterpart for randomly forced dynamical systems of the it's a geometric theory. It's like a geometric theory of ODEs, and it allows one to treat stochastic differential equations, SDEs, and more general systems driven by noise as flows in phase space cross probability space. So this is just mnemotechnical. The analogies are between SDs and ODs, between RDSs and DDS stands usually for differentiable dynamical systems, but these, what are meant are really the autonomous ones. And Ludwig Arnold, no pun intended, V.I. Arnold, okay? Although this one is much more readable than this one. I remember being invited by Ludwig, whom I had met at the Courant Institute, because everybody came through at the Courant Institute, where I stayed a little bit after the PhD that Pier Marco mentioned. So he invited me to a meeting in Germany when he got an award for studying stochastic partial differential equations in the context of climate and other applications. And although I knew his little book on linear SDEs and loved it, I found his talk really pretty incomprehensible and not terribly useful. And the consolation is that when Lai-Sun Young invited me to this meeting sponsored by INDAM in Corinaldo on hyperbolic dynamical systems, which for the first time was inviting people to talk also about applications, so I gave something like a much earlier version of this, and Stefano was there, and he even lent me his car to get to Urbino. Thank you again, Stefano, pleasant memory. You know, Lai-Sun said to me over lunch, Michael, you have to understand that even people who are on top of hyperbolic dynamical systems, you know, don't really understand these pullback attractors. So, you know, I felt much better because I didn't know how well my talk went over. Okay, so if you still don't understand after this talk, well, maybe try to go to one of the papers, because we have made a big effort in our publications with MICHEAL and Eric to explain it in as simple language as possible, but not any simpler, again, paraphrasing Einstein. So the setting is a phase space X is, for instance, Euclidean if you still deal with differential equations, a probability space, for instance, the one you're most familiar with, the Wiener space, with Wiener measure P, and a model of the noise, okay, that preserves the measure and is called the driving system. So this is the one that has to have the semi-group property that I was mentioning, okay? So as you shift by t, you know, I'll have a picture which comes out of one of the appendices of those early papers. So it starts the noise at S instead of at T, okay? And then a mapping that has a so-called co-cycle property, e.g. the solution operator of an SDE. So here comes the picture, okay, which we didn't find anywhere, certainly not in Ludwig's book, okay? A geometric view of SDE. So the idea is that these sails, okay, this and this and that, are fibers. In other words, this is X cross omega, and this is the one that happens after you've advanced by S time units, and this is the one that after you advance by S plus T units. And the co-cycle property is that going from here to here and from here to there is the same as going from here to there. Okay? So in technical language, phi is a random dynamical system or a co-cycle, and this is a flow on this bundle made up of these copies of X. Okay, so random attractor, so omega is a variable in the cap omega, it's a label of the realization. So it is both invariant and pullback attracting. Invariant says this, okay? And attracting is that if you start, as I did in the little video, from some compact set in the past, okay? And you're looking now at the yellow stuff is the random attractor, and this is a cross-section, which we called a snapshot of the pullback attractor, not knowing that Ed Ott and Chelsea Goibergi had called the whole attractor a snapshot attractor. But there's no contradiction. They didn't worry about going all the way back to minus infinity, and actually they were right, because you can show that you only have to go back and practice numerically so far. But anyhow, you start in a compact subset of your X, and you let it rip, you go forward, and things will converge to this cross-section, this snapshot of the random attractor. Okay, so I promised to say just a little bit about tipping points, because at the beginning they got on my nerves. You know, I was wondering what have these guys gotten enthused about if some social scientist came up with this word when we've been doing bifurcations all the time. But it turns out that it makes some sense to use this more general term in the context of non-autonomous or random dynamical systems, and there's actually a little classification of some of the ways that the old-fashioned bifurcation points behave, depending on the kind of process that induces the critical transition through that point. So this is a paper by Peter Ashwin and co-authors in the field of the philosophical transactions. Oops, there's 1 0 too many. So there's B-tipping or bifurcation due tipping. So slow change in the parameter leads to the system passage to a classical bifurcation. That's what we knew all the time. And then there's noise-induced tipping. Random fluctuation leads to a system crossing a attractor basin boundary. Well, we sort of also knew this about double well potentials and so on. But one that's really interesting and that people hadn't thought a lot about before is R-tipping, or so-called rate-induced tipping, in which rapid changes leads to the systems losing track of a slow change in its attractors. So it is different from this one. So all three types involve an open system, and we start with a closed system and study the bifurcation structure, then we proceed to the open ones and see how that changes things. Okay, so now we're at the climate applications. I will now proceed as one of my teachers at the Courant Institute used to. He was a very good expositor, Joe Keller, unfortunately no longer with us either, but he was a frequent visitor in Italy as well. So Joe said, when you give a colloquium talk, you start very, very slowly, and so that you still have all the audience with you for about 20 minutes. And then you accelerate until you've lost everybody by the end. Okay? So now we're at the point of acceleration, and I hope not to lose all of you at the end. So we'll start with the known Lorenz model. Sorry, was there a question?
No, I was wondering whether anyone will still be with you at the end, but you are aiming to still have someone with you. Good.
Yeah, I would hope so. Especially people who've heard this already, like Stefano Galato, and who's actually an expert and who probably knows more about it than I do, and he's also a colleague of Franco Flandalis. So you know, anyhow. So here we go with Lorenz. So a random attractor of the stochastically perturbed Lorenz system. So the interesting thing is that there was a pretty hefty literature on these non-autonomous random dynamical systems when we became interested. So our first publication at the École Normale was in 2008. And at that time, there was, I showed you the earlier references, so certainly the early 90s, the concept of a pullback attractor, you know, the existence of a global pullback attractor under certain conditions was proved by Carl and Fandoli, and there was a book by Ludwig Arnold in 1998, etc. So there was a lot of literature, and a lot of it was illegible, but there was a single numerical picture. And it was not as good as this one. It was due to Schmalfuß in the Zeitung für angewandte Mathematik und Physik, and I forget the exact year. So what we're looking at here is a snapshot. So in other words, it's one of those cross sections like this one or this one, okay? It's a snapshot of the random attractor computed at a fixed time t and for the same realization omega using different initial data and having pulled back, okay, for each, you know, having pulled back, like I said here, and you take a lot of initial data and you let it rip, okay? So we use, so it's made up of points transported by the stochastic flow from the remote past, where t is much larger than 1 being the characteristic time of the system. Use multiplicative noise in the deterministic Lorenz model with the classical parametric values that give you the strange attractor, the deterministic chaos. So the point here is you have to understand that it is very different from doing Fokker-Planck and doing, you know, forward convergence or probability density function averaged over the realizations. You have a single realization omega, and it's still very interesting. So this is the projection of the invariant probability measure at some fixed time t, fixed realization omega. So we show a projection like this, okay? And there is a multiplicative factor. So this is why it's multiplicative, because there's the xi in front of the Brownian motion, and there's an extra coefficient alpha, which is not small. So this is not a perturbative analysis. You'll see alpha can be 0.3 or 0.5, which is large for the Lorenz system. This one has 10 million of initial points, okay? And what you see here, this is where the origin lies, and this is the neighborhood. So that's the conductive equilibrium, okay? When the Rayleigh number is very small or 0, and these are the convective equilibria, which are destabilized and which in the deterministic case have limit cycles around them, and then other things happen and hell breaks loose. If you see a similarity with the cat map, as far as I know, it's fortuitous, and in any case, we don't know yet the reason for it, and I think it's an interesting question, if anybody likes this stuff. And here, again, apologies for the different aspect ratio and different color scheme, But here we have 1 billion initial data, and now you can see the beast looks even more ferocious, okay? But aside from that, what you do see is something very different from what I or anybody else thought about the effect of noise on the strange of the butterfly of the Lorenz system before. If you use additive forcing, okay, you expect essentially the Cantor set structure of the strange attractor to be smeared out by the noise and the resolution to be lost. Here what you see is there is Cantor set structure, and this is for very high resolution and explored mathematically, which is what the theory tells you. It says the invariant measure is supported singularly on the unstable manifolds of the attractor. And so we've tested this very carefully. Here's another one, again, different color scheme, but in addition, I will show you now another video which is somewhat more spectacular than the previous one, okay? So, again, what is plotted is the density. Oh, I forgot to tell you that in most of the literature, this invariant measure that is observed this way is called the disintegrated measure, which sounds very bad and very long, and we prefer the word that Lysan uses for it, which is sample measure. Okay, so what you're looking at is at this invariant sample measure, and you are going to see how it evolves in time. This is pretty dramatic, okay? You see essentially two things. One is that the measure is transported, as you see it now, by the deterministic portion of the flow. You see a GHIL, which is a pure stochastic stuff, and then you see things which are in neither, which are clearly the non-trivial interaction between the noise and the chaotic dynamics. So I'm very sad to have to stop this in the interests of time, but you can see it in two places. Where is now my... okay. You can see it either in a low resolution version as a supplementary information in this paper published in Physica D in 2011, so that was our second paper, or as a Vimeo movie on the website of MICHEAL Shekroun at UCLA. Okay, so I hope that you find this pretty fascinating. And I still have a few minutes, so I will try to show it for another model, because actually the Lorenz model is not a terribly good model to think about climate, because its spectrum is purely absolutely continuous, and there are no lines nor bumps. So you have low frequency variability in the El Niño Southern Oscillation. And that has a lot to do with what happens with the atmosphere and ocean in the tropical Pacific. I'll skip the explanation again. You can find these pictures on the web. There are two scalar indices which capture the large-scale behavior of ENSO. One is a so-called Southern Oscillation Index, which is essentially a difference of sea level pressures between the western and the eastern boundary of the tropical Pacific, or by the so-called Niño 3 index, which is the temperatures, sea surface temperatures averaged over some area around here. And you see that these two things, the Niño 3 and the SOI, are very highly anti-correlated, in spite of the fact that they're very different animals. One is the atmosphere, the other one is the ocean. They have very different spatial properties. So this really suggests not that ENSO is low dimensional, as some people naively asserted, also about the climate system in general, but there is a lot of variance in the large scales. So, Enso-Arnold in noise. So the key idea is Enso irregularity is due to the interaction of intrinsic periodicity. There is a limit cycle that would exist there in the absence of seasonal forcing, but that interacts with the seasonal cycle and with the noise. So this picture comes from essentially a PDE model. I don't have the time to go into the details, but it's a PDE model, and this diagram shows what happens, the behavior of this model with respect to two parameters, one of which is the coupling parameter between the atmosphere and the ocean, and this is a parameter that has to do with the ocean and essentially gives you the periodicity of the intrinsic variability. And the colors here indicate the periodicity of the solution at a particular point in this diagram. So black means period 1, in other words, you only see the seasonal cycle. Green means period 2, this is frequency ratio. 0.5 means period 2, and then period 3, and period 4, and period 5. And when the system is confused between two periods, essentially this is a generalization of the well-known devil's staircase. We called it the devil's bleachers or devil's terraces, and then the system goes chaotic. So what you expect is something like the Arnold tongues that arise or in the material equation or something like that. And this is the effect of the noise on the PDF of the Arnold tongue at 1/3, so one of these sections to these lines. In other words, there's a certain smearing out. And this stuff was looked at in much greater detail in a recent paper with Stefano and with his colleagues in and around Pisa, which was published last year in the Journal of Statistical Physics. And this is something that maybe Stefano will tell me during the question session, whether you've started working on this, because we had this picture which we had not published, but which is what happens when you have two standard maps coupled to each other. And you have this very fine structure of, crosswise resonances, and then you can look likewise to what happens to that in the presence of noise. Okay, we started a little bit late, so I still have a few minutes, I think. I'll try to go through the grand unification, and I think I'm going to have to skip the topological stuff, which is fascinating. Anyhow, the grand unification is, here's a classical strange attractor. So this is the Ed Lorenz view of climate. Physically closed system, model mathematically is autonomous, neither deterministic, if you want to think of the anthropogenic forcing as being deterministic, nor random, in other words, natural forcing. Clearly, volcanic eruptions are intermittent, they occur at random times. Cloud phenomena, which are subgrid scale, can be very well represented as stochastic, because we're really interested in the net effect on the larger scales, etc. So the attractor in this case is strange, but still fixed in time. So, it's analogous to an irrational number. People don't like things that they're not familiar with, so the name irrational was given because they didn't know about them before. So in this context of the Lorenz attractor, climate sensitivity is still the change in the average value first moment of the coordinates x, y, z as the parameter lambda of the system changes. You have actually numerically what you have is exponential divergence versus coarse graining. So a classical view of dynamic system theory is when you have a positive Lyapunov exponent, the trajectories, all the trajectories diverge exponentially. But the presence of multiple regimes, so in other words, the two red eyes of the beast, the two wings of the butterfly, applies a much more structured behavior in phase space. So this slide is from Lenny Smith at the London School of Economics and Oxford. You start with a PDF which is concentrated at the origin, and you move between the wings of the butterfly, but then every once in a while, you know, there's a splitting as the stuff comes down the z-axis and decides whether to go left or right. And so in the intermediate range, citing again John von Neumann as I did at the beginning, what you will see is multimodal PDFs, although eventually they will converge to a single bump at the origin. Now, random attractor, this is a physically open system, modeled mathematically as non-autonomous, etc. The attractor, so these are just 4 snapshots from that video that I showed you. The attractor is pullback and evolves in time, so it's worse than irrational. It's like an imaginary complex number. Climate sensitivity is a change in the statistical properties, first and higher order moments, including actually distribution of extremes at the attractor, as one or more parameters change. So again, this comes from a picture also from that this other encyclopedia where Lenny stuff was also published. So I have to tell you that you know, grad unification is tongue in cheek. It was suggested to me by some quote unquote press agent of one of those professional societies that Piermarco mentioned that gave me some medal. So they said, you are going to meet the press, you have to tell them something that is going to catch their attention. So I think it's actually she who came up with this term. So anyhow, what's the picture? There's a view of Lorenz, which I already explained. Climate is deterministic and autonomous, but highly nonlinear. Trajectories diverge exponentially. Forward asymptotic PDF is multimodal, at least in the intermediate range. Klaus Hasselmann Tellus, 1976. So this is the same year in which that Murray-MICHEAL paper was published. Climate is stochastic and noise-driven, but quite linear. So the trajectories might be irregular, but they decay back to the mean. Forward asymptotic PDF is multimodal. Oops, sorry. Don't forget this, grand unification. Climate is deterministic plus stochastic, as well as highly nonlinear. Internal variability and forcing interact strongly. Change in sensitivity refer to both mean and higher moments. What you're looking at here is also coming from an ENSO model that I won't have the time to show to you, but I can share the slides with Fabio if you like. This is again one snapshot in the embedding space of a variable of the model, the depth of the so-called seasonal thermocline, h of t, and h of t plus 1. And so again, there is this filamental structure and very irregular distribution. And these things change either in time or with parameter or both. So I'm going to have to skip the work in progress, and I'll be happy to answer questions. I'll also have to, this is, you know, dedicated to Poincaré, after whom the institute where we had that nice meeting was held. And I'm going to have to skip these in the interest of time. And again, just pass to the concluding remarks and the bibliography. So summary, a change of paradigm from closed autonomous systems to open non-autonomous ones. Random attractors are spectacular. I hope you'll agree after seeing that video. Useful, I think we're starting to show that they help really shed light on the underlying phenomena in the presence of time dependence, and still just starting to be explored for climate applications. Work in progress, study the effect of specific stochastic parameterizations. I told you that the subgrid scale phenomena should really be parameterized stochastically, but until recently that wasn't the case. They were really parameterized deterministically, and now that they are parameterized stochastically, still nobody looks. People look at the effect that it has on the simulations, so the large-scale simulations of the big model, but not how the behavior of the big model is modified systematically by such things. Okay, specific on-model robustness, applications to intermediate models and general circulation models, implications for climate sensitivity, for predictability, that again I didn't have the time to discuss with you. They'll just leave you with some general references. So one of the slides was taken from this work, which is done with Stefano Pierini in Napoli. And so this was a paper dedicated to the 90th birthday of Peter Lax, applying dynamical system theory to a climate problem and DCDS. And this is the paper that Stefano Galatolo was asking me earlier. So this is really in press. It should come out any day, or at least within a week or two. We've gone already through 2 rounds of proofs. And here are some of the other things that I mentioned. You have at least something to dip into the literature with. So this is the paper with Valerio, and I'm done. Thank you very much.
Thank you.
I'm trying to get out of this so that I can see.
Yeah, that's good.
Okay.
There it is.
Okay, thank you, Michael, for this nice talk. Very stimulating. And let's see if there is anybody who has questions or comments. Maybe.
Some question, Piermarco. Sono Francesco.
Sì.
I'm just asking. You said somewhere that there is an action on the time, maybe, on the sample space, the probability space, as a measure preserving transformation. Right. Is such an action assumed to be ergodic?
Well, it will not be ergodic. Okay, that's a very good question. Thank you very much. We were able, in the case of that highly simplified wind-driven ocean circulation model, to prove that there is a global compact attractor. There's dispertivity and there's a global compact attractor, but numerically, they are observed very clearly the coexistence of 2 local attractors with very different stability properties. In other words, one is quiescent. This is going to take time because should I share again the screen to show you that? Because I have the slide. Is that okay? Sorry. Okay. Right. I have to find it. Here you go. Okay. Okay. So what is plotted here is not invariant measure. It's a measure of divergence of trajectories for each initial point in a plane of this 4-dimensional space in which this system evolves. And you see that there are points, clearly the warm colors correspond to agitated behavior, and the cold colors correspond to calm behavior, okay? And the 2 plots are for 2 parameter values, which measure essentially the time constant component of the forcing. So in the absence of the time-dependent forcing that I was mentioning on one of the slides, basically these 2 panels lie on either side of a classical bifurcation. A classical bifurcation that occurs between a small limit cycle and a large relaxation oscillation. In the presence of the noise, what you see is that the space occupied and the nature of the agitation, increases as you go through that thing which becomes a tipping point. Okay? Francesco.
So you are saying that to assume ergodicity is not a good thing?
Well, it depends for what. I'm sure it's an excellent thing for a lot of applications, including possibly in climate. Not everything in climate is bi or multimodal, but assuming it a priori for a model that you don't know very much about is not a good idea.
Yeah. Thank you.
Okay.
Let's see if there is anybody else.
Yes, can I make a question?
Sure, please.
Yes, my name is Alessandra Celletti. So thank you very much for your very nice talk. Let me say that I work on dissipative systems since several years, but more on the field of celestial mechanics, precisely on satellite subjects to tidal torques. And, also from the theoretical point of view, we did several works with Rafael de la Llave and Renato Calleja on a subset of dissipative systems which are called conformally symplectic systems. So we don't have stochastic, we don't have noise, we have deterministic dissipative systems. And I wonder if you can answer some questions which trouble me since several years, let's say. So one of the major problems I find, especially when doing numerical computations, is to evaluate the transition time to land on the attractor. So you showed some snapshot.
Repeat, transition time, that I didn't hear the words after.
To land on the attractor, to arrive on the attractor. Because you show in your talk, you showed some snapshots at a given time. But in fact, do you know whether the system is already in its, let's say, close to its asymptotic behavior? That is, it is close to the attractor. Or can you give a measure of the transition time that you need to go to the attractor? This is especially important when you are in the symplectic limit, in the weakly dissipative regime, let's say. The second question is that you mentioned the Arnold tongues, which I expect you computed in the stochastic system, so in a system adding noise. And can you specify me whether it is, you mentioned the two coupled maps, are they standard maps or Arnold maps? So
that picture, which reminds me somewhat of what is called, I used to show it many years ago when we were working on that early work, along with a picture of a French garden, you know, with the nice alleys which intersect at straight angles and so on, you know, including diagonals and so on. Yeah, those were standard circle maps. And I don't know, Stefano, you want to say something about whether there's some work now proceeding on that, or?
You mean about what? This is a system which comes from the interaction of these circle maps and noise, and at the end is a map of the circle plus noise. So at the very end, this is a simple system, but still showing.
No, we talked, Stefano. We talked with you and Angelo about the possibility of, you know, at some point doing really two coupled circle maps, which are both active. It's not that you're averaging over one of them. Okay, so
no, this is technically possible, but we did not do it. That is like a mathematical result. To get mathematical result,
yeah, I know.
I think it's possible, but it's a bit more complicated.
I think it's not trivial if you increase the dimension of the phase space.
No, let me then answer your question more directly. I would appreciate it if you sent me an email, because I've actually done work going back to 1992, published in SciApp, with one of my last students at the Courant Institute, Gershon Volansky, who's been a professor.
I know the paper very well. It is one of my favorites. So
I'm so delighted. I didn't think that anybody, you know, is still looking at that. But so I know a little bit about dissipativity. You know, the standard assumption for people who haven't looked at it is, of course, that celestial mechanics is why Hamiltonian dynamics was invented. But there is small dissipation and so on. And we've done a lot of follow-up work with Gershon and with Ferenc Varadi, who unfortunately passed away some years ago, fairly young, of a heart attack, who was both my student and my postdoc at UCLA. on both on protoplanetary disks and a lot of other stuff, and with Bill Cowler, who was one of the greats of the field on the great inequality and so on. So I don't know whether you know that work.
Yeah, sure. Yes.
But your immediate question, we are working. We have a paper under review in Physics Review Letters with Yuzuru Sato as lead author and MICHEAL Shekrun as the third member of the team, not in order of importance, in which we look exactly at this question. You know, I've been preoccupied by that. I mean, numerically, we of course had to cope with that in the first papers with Michael and with Eric, 2008 and 2011, where we dealt with the circle map, and then with the Lorenz with Laura. So, but in this paper with Yuzuru, who happened to be a visitor at Imperial College when I was occupying a visiting position in the math department there. So to determine more precisely how to know in advance how far you have to pull back. Yeah. So don't hold your breath. You might go blue in the face because this thing has been going on with Yuzuru for a long time, but we were really supposed to do the revised version last month, but you know what happened between March and last month, so it's not done yet. But please stay tuned.
Okay, thank you. Thank you very much. So I will send you an email, by the way.
Okay, and tell me what you don't know. Because
okay.
Well, it looks like you know already some of these papers, so okay. Thank you.
Okay, thank you.
If I may add a very small comment on this, which is related also to the work that Michael mentioned before on the ENSO model. What happened and what generates this irregularity, like Arnold tongues and so on, is that well, in that paper we are looking to invariant measure, stationary measure for the random system. And what happened is that the convergence to equilibrium to the system, of course, if you look at the transfer operator, which is associated, the speed of convergence to equilibrium depends on the spectrum. So, and what happened is that there are eigenvalues coming to radius 1 according to if the arithmetical properties of the system approach a periodic one. So if you want to measure the speed of convergence to the equilibrium, you can look at the transfer operator and see the eigenvalues. But this is maybe a too general and stupid remark, but this is the source of what you see in this picture.
Yeah,
in our case,
Stefan, sorry, this is clear to me. When you have a circle map or even two coupled circle maps, I have problems in celestial mechanics which are more dimensional, and in that case it is not trivial at all to measure even the Lyapunov exponents and the transient time. That was the question, because especially because you have a fractal basins of attraction, for example, and periodic orbits in the small dissipation limit become extremely entangled, and so it is difficult to give a reliable measure of this transient time.
Yeah, actually the big surprise in that paper with Gershon Volansky was that on the intermediate time scale we were getting a strange attractor. So that is essentially related to what you are talking about.
Okay, well, let's see if there is anybody else who wants to ask a question. Otherwise, I think we have been, well, going on long enough today. And so I'm glad we managed to have this event. And I thank again Michael for his talk, all of you for attending the colloquium, and maybe, hopefully, we can meet again for a talk on this topic in presence in a year or so.
Spero davvero di rivederci in persona e a Roma.
Yes, yeah.
Stay
Waiting for you.
Okay, thank you very much for inviting me.
Okay. Bye-bye, everybody.
Bye-bye.
Bye-bye.